Welcome to our webinar today. It's going to be a short session. I'm going to take about half an hour, so that leaves you about half an hour during your lunchtime today. My name is Sashi. I am part of the simulation and plastics team here at CAD Dimensions. And the goal of today's presentation is to go over specifically birefringence analysis within SolidWorks Plastics. As many of you know that are on this webinar today, actually see many familiar names. The photonic industry is growing in upstate New York, which is where our primary customer base is located. And with photonic applications, there are many parts which would require injection molding and can experience birefringence. So SolidWorks, so again, the goal here today is to show you how to take those parts that you will be creating within SolidWorks, those 3D CAD parts, and running an analysis within SolidWorks Plastics to see how it will injection mold and what type of birefringence you will get from the type of geometry or the injection molding properties that you use to set up. And based on that, you can either change certain injection molding properties or even the geometry to reduce the birefringence and get better parts. So to jump into this, let's quickly answer the question: what is birefringence? It's a phenomenon that typically can be seen in optical properties, which is transparent, such as this part that you see down here. You can see these shiny areas. That is what we call birefringence. Now, if there's too much of these type of scenario found on your plastic part, that can cause it can be difficult to see through the part, and it could defeat the purpose of that application itself. So you can see in plastics this affects the light transmission or clarity of the image being transmitted through the part. And typically this birefringence is caused by the residual stresses in the part after molding. Now, what's nice about SolidWorks Plastics is that you'll be able to see how birefringence is being created within your part at different stages in the injection molding process. Now, in a physical environment, you'll probably only be able to test for birefringence using your physical testing setup once the part has been molded and ejected from the injection molding machine. Using SolidWorks Plastics, you'll be able to see birefringence at the end of the different stages in your injection molding process, at the end of filling, the end of pack, and of course at the end of warping as well. And within the warp analysis, you'll be able to see the combination of thermal induced birefringence and as well as residual stresses, birefringence caused by residual stress, and as well as the combination of those two. So it actually gives you more information than you can find in a physical environment, which then allows you to better dissect and evaluate which areas might be better for you to set up physical properties. Because as you know, physical properties for your injection molding machine changes from process to process within the injection molding cycle. So you might change the initial injection pressure or the pack hole pressure, depending on what you're looking to do and how you plan on reducing this birefringence. So just a little bit more information on birefringence. The direction of stress. So when the light strikes a planar surface, it creates two components, an ordinary and extraordinary ray. Material having two different indices of refraction in different directions. So birefringence is also known as double refraction in the industry. So within SolidWorks plastics, just to give you a quick view of the type of results that you can get, the results are actually broken down into three different planes. So you'll be able to view birefringence if the light direction comes from the XY, so either the XY, XZ, or YZ direction. So you can really dissect and view the birefringence results throughout your part. All right, so now let's go ahead and look at SolidWorks plastics and what is required from the standpoint of SolidWorks plastics in terms of material. So when you're running a SolidWorks plastics analysis, typically you will only need the basic plastics materials to evaluate how the part will perform during the injection molding process. As you know, SolidWorks plastics allow you to see how the part will be filled, how the part will react to the pack hole phase, and how the part will warp, as well as you'll be able to add cooling lines to see how different cooling lines and cooling channels might affect your warping analysis. Well, when it comes to birefringence analysis, you do have to add some additional information to get the results. So within birefringence material, there are three properties, and the way it works is you'd either have to have the presence of a Leonov equation, WLF equation, and or the stress optical coefficient. Typically, the stress optical coefficient is much easily obtained. That can be done by sending your plastic pellets to a test lab, and they would be able to evaluate and give you that information. The Leonov and WLF equation can actually be found fairly easily from a lot of research that we've done. Basically, these numbers are the same as long as you're within the same plastic family. And I'll show you an example of some of the coefficients that we've gathered with working with SolidWorks in gathering this information. So when it comes to birefringence, obviously for the most part you would be looking at a transparent part. So you want to be able to have the light transmit through the part, based on that you'll be able to get the right results in SolidWorks plastics. All right, so this is just additional information to the Leonov parameter and the WLF parameter. So we'll take a look at how to input this within SolidWorks plastics. I'll show you exactly where it is within SolidWorks plastics. And this is the stress optical coefficient. Again, this is the window. So for some of you who are familiar with editing material within SolidWorks plastics, you'll actually see this view, and under the others tab you'll be able to put in that information. So this is the stress optical coefficient above your glass transition temperature, and then this is below the glass transition temperature, and it will show up within the materials information layout, showing you that information right there based on what you input here. All right, so here's the view of all the examples of a few material that we have the information, whether it's a LWF parameter or Leonov parameter. For some material, we actually have all three, so we even have a stress optical coefficient. So you can actually see, and the reason why I put this slide up is I wanted to show you that the WLF parameter for all these different materials is actually the same number. Now the reason is because they're all under the PC polycarbonate family material. And then we have our PS family material, and you can see the numbers do change for your C1, C2, and the T reference. It does change, but it's the same within that that family. Now, one thing that you will see is that the stress optical coefficient does change. So you will see that for this ACM material, it does have a different stress optical coefficient, and for the 2PC material here, it's similar, but then when you have a PC plus ABS, that does change somewhat. So again, this is more more precise. You get much better results, and this can be you can get this information from a test lab that will be able to test your material and give you that information. And if not, then you can put in this subscribed WLF parameter and Leonov parameter, and you can get pretty close to actual actual results. All right, so I do have a question here. The first row is V825 is acrylic, not polycarbonate. Why does it have the same value? That's a great question. So these are parameters that I've gotten from directly from SolidWorks, and you're right. I actually did realize that as I was looking at this. So that's a great question that I can bring back to SolidWorks. However, for the most part, material within the same family will have the same WLF and Leonov parameter, and there might be a change in the stress optical coefficient if there is a addition to that material type. Okay, so again, great question as to the acrylic. Why does it have the same parameters? I can definitely find out and get back to you on that when you do reach out to us. All right, so let's continue on with this. All right, so this is typically how you would set up the birefringence analysis to take place within SolidWorks Plastics. So what I'll do is I'll jump into SolidWorks right now, and then I'll come back and we'll kind of review this and talk a little bit more about some of the information that we see on this page. So what I have here is you can see that this is an optical part. This is a part that I really like to use for birefringence analysis, and the reason because it has a lot of curved geometry, which typically is present in a lot of optical or medical device applications. And you can see that obviously that I've set the appearance to look like it's transparent, just to get it as close as possible to real view. Now within SolidWorks Plastics, for the most part, the setup for the fill settings, pack settings, and warp settings is exactly the same. Actually, the pack and warp settings do not change for your regular setup of SolidWorks Plastics. The two changes is your polymer, your material type, and of course your within your fill setting you would have to invoke the viscoelastic birefringence analysis checkbox so that SolidWorks will run the analysis. So let's go ahead and look at how to set up this material for birefringence. And when you right-click any material within SolidWorks Plastics, obviously this would be under your user-defined database. So one thing that you could do is you could come into the default database, and let's see if I look at one of the PCs right here. And if you look at some of the information here, this already actually has stress optical coefficient set up for us, so that's helpful. And it also has your Leonov and WLF parameter already inputted for us. So this for the most part has, so if you pick one that doesn't, let's see. So these don't have any information and you would like to input that information, all you need to do is just right click and copy it, come into your user defined database, and you just paste that material right here and you'd be able to come in here and edit that material. So let's see, it was this, and you say edit material, and that will bring you to this page where you can start off with your viscoelastic parameters, and you can say Leonov viscoelastic model, and you can put in all those parameters right here. Now if you have this information, that's great, you can input it here. Now if you want to put in your stress optical coefficient, it's under your others tab, and it is located right here. So you can put in above TG and below TG. Okay, so once you have all this information in place, and again you need either or. If you have both, that's great as well. SolidWorks will probably take into account both and shoot out probably the best results that you can get if you have a combination of both. But to get your birefringence results, you really only need one or the other. Okay, so that is your input for the polymer. Now for the fill settings, we can take a look at turning on birefringence analysis. So SolidWorks Plastics will not run birefringence analysis unless you ask it to. And the reason is because if you do turn on birefringence analysis, the analysis will take a little extra time because it needs to take into account that information. So under your advanced tab right here, you do have a check mark, viscoelastic birefringence calculation. Make sure this is checked. You say okay. You come in here, you right click this and you hit run. That will run your analysis and it will calculate birefringence for your flow, pack, and warp analysis. So for the last 10 minutes of this webinar, I just wanted to quickly go over the results that we can get from running this analysis. So this will take a little bit of time. Essentially what this is doing is it's reading up all the results. So what I'll do is before I jump into the birefringence results, I'll just show you how this part filled. Just keep in mind that I'm not a plastics expert, so this is my best guess as to how this part would fill. I'm sure a lot of you out there could figure out a much better way to fill this part. So just keep that in mind. The birefringence results we get might be exaggerated somewhat here because of the way this part is being filled. Just from the animation of how it's being filled, I can probably tell that there's probably a better way of filling this part in, just because of how it slows down up here. But for the most part, I do get a pretty balanced fill right down the middle. So you probably see some knit lines down the middle here. But what is interesting is that you could see how the polymer is forming together in the middle here, and that will affect the birefringence results that we get as we look at it in a second, and primarily for the packing phase. So within the flow analysis, the birefringence that you get when your light shows from the XY, XZ, and YZ is actually the same, because at this point all you're evaluating is the total birefringence at the end of fill before we move into the packing and whole phase. So if you look here, as we navigate through the different results. So we give it a second here. It's just reading the results. As we navigate through the different results here, what we get is actually very similar. So I hope this is transmitting across right, because we are on a web meeting. All right, so there we go. I was just thinking for a second. And you can see that when I change between the XY, XZ, and YZ, my results actually don't vary. It's giving me the same results, but you can actually see or start to get some idea as to what the birefringence is going to look like. Okay, so the next step to this is we can actually see the pack the birefringence results at the end of pack. And so XY plane. So again, we'll give it a second here. It's just thinking. The XZ plane. You can see how it actually changes now in your packing phase. And for our YZ plane, again, just give it a second here. It's just thinking. So typically it doesn't take this long. It's pretty fast, and really the reason is because we are on a web meeting. So let's see. All right. So what we can do is probably switch to the warp. The warp results. It's also still reading in. You can see down here. And you can see under your warp analysis, there's a good number of birefringence results. And as I mentioned earlier, you'll be able to see your flow stress-induced birefringence, and as well as your thermal stress-induced birefringence, and then the combination of those two for your XY, XZ, and YZ. So this is where you actually should be able to see the difference in results based on the light location. So we'll start with the XY plane flow stress induced. So typically when you look at a red part in analysis, it's bad, but actually it's not that bad. What you get here is actually 0 for the most part in your part, which is good. Besides just this one area right here, which if you recall, this is where that plastic came together. And if you look at the XZ plane, it's the same thing. We're actually getting 0 results, except again for that one area. So in real world, this is probably an area that you would probably need to reevaluate how the plastic is flowing in, or maybe reevaluate how the geometry in that area might change. If you look at our YZ plane, it's again going transparent. Let's see. Okay. So you can give it a second to think here. Maybe I can just reread the results. All right, so let's take a look at this again. I just basically reread the result. So this is the XZ flow stress induced birefringence. The XY stress induced for all three, and then the total. So just to rotate so you can see it clearly how it looks. Right here again. So this is for if the light is reflecting from the XZ. So use your triad to your advantage. So XZ. Essentially what this is showing is that if the light is in this direction, this is the result that you will get, and YZ. So YZ, you can see right here, so the light is shining in this direction. This is the results that you will get. Okay, so almost at the end of this webinar. Before I exit out of this, any questions? You can just quickly type it in, and maybe we can take a look at some of the results. And again, I'll just scroll through all the different results so you can take a look at it again. All right, so a couple more slides, and then we can wrap this up. Flow-induced birefringence. So again, there are two types of birefringence that can be evaluated: flow-induced birefringence and thermal-induced birefringence. Flow-induced is created by flow-induced residual stress, and thermal is created from thermal-induced residual stresses. So we did get a question: is there a view that will simulate the visual results of looking at a part between cross polarized, similar to the photo you showed earlier in the presentation? So I'm assuming you're talking about this. This is let's see, there should be a way of doing this, because this was taken as part of the as part of SolidWorks plastics. So if we look at clipping, all right. So again, again, a really good question. The photo of the molded part in front of your computer screen. So I'm not really sure if I understand the question. Nicholas, I will reach out to you after this webinar. Maybe we can talk about this a little further, just for time's sake. So just to wrap this up, meaning of the different results that we just looked at. So birefringence at filling end, this results as not only involve frozen region but also contains non-frozen region birefringence, right? Because it is before the pack hole phase, before the plastic completely solidifies. Birefringence at packing end results also contains non-frozen region birefringence. Flow stress induced birefringence only contains frozen region at filling and packing stages. All right, so again, so here's a view where you can actually see how this part was done. This part was analyzed within SolidWorks Plastics, and you can view the results in reference to real world. Pretty close, gives you a really good representation of how the results will look before you actually go and cut your mold for the injection molding process. A great way to reduce your reworks. All right, so if you have any questions, again, I wanted to wrap this up and keep this within the half an hour time. So if you have any questions, please feel free to email me, sashi@catdimensions.com, or you can also call us at 877-223-4255. You can ask for me, and I'll be more than happy to talk to you about SolidWorks Plastics and Birefringence analysis and some of its capabilities. And of course, visit our website to view more webinars like this that have been recorded in the past, and you'll be able to view it. All right, so that's all I have for today. Thank you all for joining me, and enjoy the rest of your day.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.